Hello everyone. In this video, I'll be discussing about the concept of potential in relation to the work done, which we have discussed in the previous videos. So if I consider a circuit, and in this, in order to have a current flow, the charges should flow from one point to another point. Let us consider the charges here in this case is electrons. The electrons will move from this negative terminal of this supply and it will go through this entire circuit and come back to the positive terminal to complete the circuit. And we also know the direction of conventional current is opposite to the direction of charge flow. So we usually consider the direction of current is from positive terminal to the negative terminal of the supply voltage. But the actual flow of charges is from this negative terminal to the positive terminal through this closed path provided by the circuit. And also we know for the charges to move from one point to another point in the circuit, we need some force or energy to move this charge. We have already discussed about how much amount of work is required to move a charge from one point to another in an electric field. Now here, there is the work done by this supply. This supply is called as the source, which is providing the energy to move the charged particle from one point to another point in this electric circuit. And hereby we can call this as the potential, and this power supply is also called as the potential source for the charges to flow. We can now define the potential in terms of this work done. We know the potential can be defined as work done per unit positive charge. If I consider for a 1 coulomb of charge or plus 1 coulomb of charge, how much of work is required to be done to move the charge, that is called as the potential. Now here the potential and work done is defined in circuit concept. Let us now define the work done and potential in the electric field concept. We have already discussed work done in moving the charge from point A to point B against this force of electric field can be given as minus Q line integral E dot dl. Initial point is A and final point is B. Now, as per the definition of potential difference, if I find difference in potential between the 2 points A and B, that can be defined as the amount of work done in moving the charge from point A to B per unit positive charge. And we can define this potential difference as work done by an external source in moving a unit positive charge from one point to another in an electric field. Mathematically, we can give the expression as work done per unit charge. And you should also note the convention here. Potential difference VBA indicates the charge is moved from point A to point B, where initial position is A and the final position is B. And we can write potential difference as work done per unit positive charge, and we can write in terms of integration over this electric field intensity, where the charge is moved from point A to B with the convention of potential difference as VBA. We can also say this initial point is the reference, where with respect to this reference, potential at B is measured. So we can write VBA as potential difference between VBA, where A is the reference and the potential is measured at B. We can also relate this to how we are measuring the potential difference using a voltmeter. We will have one reference terminal or ground connection. With respect to that ground connection, we will measure the potential. So here we are considering potential difference between 2 points where the initial position is A and final position is B, and thereby the potential difference is defined as VBA. In case if I'm measuring the potential at the point A alone, or the potential is measured at the point B alone, in that case we will define those potentials as absolute potentials. Absolute potential at point B or absolute potential at point A can be defined as the potential at the point with reference to the point where zero potential is available. We know usually the zero reference is considered at the ground in case of circuit concepts. If I consider here, this reference is the ground, where the zero reference is taken at ground. And in this case of fields, nearby this area, we don't know where zero potential is available. So we can consider the zero potential or zero reference is available at some infinite point. With reference to this point at infinity, where zero reference is available. We can consider this ground or zero reference is available at an unknown point at infinity. With reference to this infinity, if I measure the potential at A, practically if I say the voltmeter's positive terminal will be kept at point A and the negative terminal will be kept at the ground, thereby we will measure the potential at the node A. Similarly here, if I measure the potential at point A with reference to the potential at infinity, then that defines the absolute potential at point A, where the initial reference is at infinity and the final point is A. In terms of integral equation, we can give this as line integration. Initial point is at infinity and final point is at A. This gives the absolute potential at point A. Similarly, we can give the absolute potential at point B by taking initial reference at infinity and final position at point B. So these two gives the absolute potentials at point A with respect to zero reference, which is at infinite point, and absolute potential at point B with reference to zero reference at infinite point. Now, in terms of these two absolute potentials, we can find the difference in potential between point A and B. That is, VBA can be written as VB minus VA. If I know the potential at B and if I know the potential at A, difference of these two will give this actual VBA, which we are trying to measure by taking integration with initial point A and final point B. So this can be proved by taking the intermediate point at infinity. We have already discussed potential or work done is irrespective of the path chosen. We know if work done is irrespective of the path chosen, potential also is irrespective of the path chosen. Now, instead of going through a straight line from point A to B, if I consider an intermediate point at infinity, from A, if I take to infinity and from infinity to B, if I go around, then we can prove that this VBA is VB minus VA. So let us consider an intermediate point at infinity. So if I try to write VBA, it is actually from point A to point B. This can be segregated into two integrations, one from A to infinity and another from infinity to B. If I write that way, this VBA can be written as minus one integration is from A to infinity and addition of another integration from infinity to B. So now we can make use of this general expressions for absolute potential in writing this difference in potential. So we can write this A to infinity in terms of this VA. So the limits of integration should be interchanged to write in terms of VA. So if I interchange this limits, there will be one negative sign coming to this integral. So we can write that as change in limits with one negative sign. And the second integration also will carry the negative sign, which is common from here. Now we can write this as VA and this can be written as VB. So we will write minus of VA plus VB, which gives VB minus VA. Thereby, we can prove the difference in absolute potentials at VB and VA will give the difference in potential between the 2 points VBA. So that is the ultimate understanding of absolute potential and potential difference between the 2 points in terms of work done. Thank you for watching the video.